See if it dings this time. Hey, it dinged. All right. Cool. So this is question number 2, 2019 again. Let me jump in and show you a couple of the earlier ones. The first one's a picture. That's nice. I think that's about as easy as life gets. When you have to do pictures on the AP chemistry test, it's usually like ridiculously simple, assuming you can count and assuming you understand what you're attempting to draw on the other side, right? So let's get our bearings. I have this reaction up above. I have 4 molecules of hydrogen peroxide because they told me that the little colored in circles are my hydrogens and the open circles are my oxygens. So all I need to do is produce the products of H2O and O2 and make sure the ratio is correct, right? And I cannot create any more atoms than they've given me, and I cannot destroy any of the atoms they've given me. So if I've got 8 oxygens to work with over here, I need to have 8 oxygen atoms over there, obviously in the product format, but I think this is pretty simple. I hope. I need 1, 2, 3, 4 Mickey Mouses. Fourth one's got an ear issue, but okay. And I then have an additional 4 oxygen atoms that still need to get drawn. That's my other product, right? 1, 2. I think that's what you got. Because again, the ratio is 2 to 1, right? Coefficients 2 and 2. So if I had 4 hydrogen peroxides, I should totally make 4 waters. And my coefficient of oxygen is half of that, so I should have half of it. I think that's easy.
It doesn't matter how they look, right?
Well, clearly no.
Okay.
Yes, no, it doesn't. No. The order, where you draw them, how beautiful you have drawn them, whether or not you've shaded in depth to show 3 dimensions, please don't waste your time doing that. No, it doesn't matter. Yes, if you physically have what you're supposed to have, you're good. Questions? Nice and easy, right? That's like a good way to start a problem. Feels good. Okay. B. Shown below is a potential energy diagram for the uncatalyzed decomposition of our hydrogen peroxide. According to the diagram, is the decomposition reaction exothermic or endothermic? Justify your answer. Now, this is where we start. This is where we end. Reactants, products. From this plateau down to that plateau, sorry, it's not drawn perfectly, is what's known as our change in energy, right? We were previously higher, we are now lower. Delta E is negative, meaning energy is lost, meaning we have an exothermic process, right? So this is exothermic. Why? The potential energy of my reactants is higher than the potential energy of my products, aka energy has been lost throughout the process. Yeah, it's as simple as that. I'm gonna use the term potential energy as my y-axis and my term that I'm going to use in my explanation. So I will literally say exothermic. The potential energy of the products, or sorry, of the products. I want those other boards. And that's enough. Okay, I could add an additional sentence, obviously stating, you know, this means that energy was lost, but it's very, very strongly implied, and it should be good to go. Yes. Probably. Yeah, I mean, and again, this is where like the grader comes in. Let me read you AP's explanation just to kind of give you what their official answer is. This reaction is exothermic because the products have lower potential energy than the reactants, thus the system lost potential energy releasing heat.
You said that as the reaction went on, there was less. There was like less potential energy.
Yeah, that'd be fine too, right? Because our reaction, or x-axis is reaction progress. So yes, as the reaction progresses, there's less potential energy in the system.
Yeah, I'm just I was wondering about like whether or not it's like the like specific words they use to make like like what's the product.
Maybe. Maybe. I've never graded an AP chemistry test, so I honestly cannot say where those like sticking points are. But I'm sure, like in certain scenarios, my guess is they're probably not too stickler on this one. Like if you say it's exothermic and you provide at least some sort of attempt at an explanation, I'm assuming they're giving you the credit here. It's hard to know, I guess. Stella?
You could just say, so like the potential energy being released during-
That would work. Yep. Yep. Because that's what exothermic means, right? We are releasing energy. Yeah. 2B2. Sorry, I mean this one. Normally, what I've been doing, right, is I've clumped them all together, and then like I'm writing out like which part I'm on, and I do recommend you do that as well. This one's for whatever reason this one's very separated, so I'm just kind of writing my answers underneath those questions. But manganese dioxide is an insoluble substance that acts as a catalyst for the decomposition reaction. On the diagram above, draw a curve to represent the reaction as it occurs in the presence of MnO2. Well, this is second semester, I think, right? We were doing this in Unit 6, I believe. We have a reaction. And if I've added a catalyst, what does that do to my reaction? Lowers the activation energy. Be very, very careful when you draw this in. A couple things you want to be extremely cautious of. The reactants and the products are quite literally going to be at the exact same energy. We have not changed the initial potential energy of the reactants, and we have not changed the final potential energy of the products. You must finish on the same plateaus. The hill is shortened. That's the difference.
Does the reaction speed up as well? So it should be like
Yes.
somewhat shifted to the left, or like
No, this shows nothing of, no, don't do any of that. Don't worry about kinetics. This is not a kinetics question. This is a potential energy question, more or less. Yes, Stella?
Because there's the catalyst, and then what was the
Inhibitor?
yeah.
So when we didn't talk about that a ton, but yes, reactions can be inhibited as well. There's a substance that you can add to like slow it down,
Oh, okay.
but we're not doing that.
No, I know. I was just wondering what would happen. Just so like.
So if we inhibited a reaction, it's one of a couple things. Sorry, yeah, they're guarding over there. If you inhibit a reaction, you could actually do it a couple different ways, right? If there's a way to lower the potential energy of your reactants, or just like shift both of these plateaus down, then you've obviously raised the potential or the activation energy. Or yeah, you could add a substance that actually requires a greater amount of activation energy to have it go. But that's beyond the scope. So we'll stop talking. Yeah, and that's it. Now, if you wanted to label that, right, maybe you could. You should maybe like be like, this is the MnO2 reaction, something like that, right? That's maybe a little overkill because they obviously are looking for you to draw something on the graph. And if you've drawn something on the graph, I have a hunch they'll realize what that's for. But no, it never hurts to be very, very organized and very, very complete in your thoughts, in your representation of your answers, because that helps the grader a ton. All right, brand new scenario. A student investigates the decomposition reaction in the laboratory. The student prepares 2 small beakers, adding 20 milliliters of 9.77 molar hydrogen peroxide to each one. Each beaker is placed on an electric balance. The student adds 0.10 grams of manganese dioxide to the second beaker and records the mass of each beaker and its contents at 10-second intervals for 1 minute. The beakers and the data are shown below. Hydrogen peroxide, nothing in it. Hydrogen peroxide, catalyst added. They monitor the mass over the course of 60 seconds. Okay, what's our question? For beaker 2, during the 60-second period, calculate the following. The number of moles of oxygen that was produced. All right, what we have over here is mass. Okay, we have an initial mass of our beaker with our stuff and a final mass after 60 seconds. Now, the difference between those two is going to be our oxygen. Okay, we are losing mass. Well, what is it? It's this product right here, right? We have lost oxygen gas as this substance decomposes. So the difference between where I started and at 60 seconds, that difference in mass must be from the loss of oxygen and nothing else. Does that make sense? Maybe that's the hardest part of this problem. Once you realize what the quantity that you need to work with is, it's factor label. We're on to just doing grams to moles. And then part C2 is going from the moles of the oxygen that we previously solved to the mass of hydrogen peroxide using the balanced chemical equation. These are back-to-back factor label problems in this part of the test, or in this part of the question. So, have you finished that? Are you past that or beyond that? If you're chilling and you're waiting for me to do more, and if you're not done, keep going. Okay, I'll write these out. You're more than welcome to pay attention as I write these out. But if you're not done with this problem, or if you haven't attempted all sections, keep going. I'll give you kind of a half time, and then I'll jump back in and show you the rest. Okay, I'll write these up now. And, yeah. Now, here's my answer to these two chunks. How many sig figs should that answer be?
3.
Well, no,
Wow.
I'm asking you like legitimately. How many should it be?
2.
2. If I write 3, who cares? We're good. Okay. Again, now, if you really want to do sig figs, you can, I guess. But in reality, 3 is going to work. I promise you. Okay.
If it doesn't work, am I going to be able to hold you accountable for that, Mr. Robinson?
Yeah. This is going to work. Because that's how they grade.
What if the answer says use sig fig, or the question says use sig figs? Then I use
That,
sig
in
figs.
all honesty, as dumb as this sounds, even when it says use appropriate sig figs, they generally give credit for plus or minus 1 sig fig. Now, not always. Maybe at the end of the day, if the question specifically asks for significant figures, there's a decent chance they're going to pick 3 anyway.
Yeah.
But if it does specifically ask for some sig figs and you know what it is, use the right amount, right? Don't purposely buck the system when you know what the correct answer is, I guess. But when in doubt, go 3. That's always the truth. Yes. They won't do the sig fig. They won't acknowledge. Yeah, they won't do the whole sig fig nonsense with pH.
Promise me on that?
But you're right. The appropriate number of sig figs in a pH would be the decimal places.
You want to promise me on that, Mr. Boston?
Yes. I think
Then sounds super confident.
you're right. Or did it? Keep going, please. I'll pick up D through G in a little bit. Again, this is more useful and more powerful if you're trying. So I'll try to pace myself appropriately.
Here's one of questions that I was wondering about. Like this one here.
So this is Q versus K.
Yeah.
Right? So if you have,
I was just wondering because I didn't know how like the solution that they had broke down.
so these are KSP reactions, right? So KSP is always a solid substance, equilibrium, like breaking down.
Yeah.
This is a solid. So when I set up K, it's really for oxide. So this K value is really going to equal.
Not zero, it's better.
Yeah, I got that. My problem was it's like how would it like compare? Because like the same substance is being split up between the two.
Yeah, okay, so yeah, correct, because they're adding salt. And the question is, so if you decide to make
Instead of justify it, yeah.
this threshold, not precipitation. So the question is, okay, well, let me plug in the concentration.
No.
Say you disagree.
Yeah.
And if I multiply this out in my head, it's greater than this.
Because now we know that it's split between the two, it doesn't matter.
Because there's no precipitation. Only precipitation happens, yeah, some talking about change in concentration and then affected.
It's
But
second
prior to
order.
that,
I
maybe
don't
it's
know how
equal.
to explain it.
How you know second order?
I don't really know.
And if it's greater than, then it has to shift.
Correct. If you're using a Q's mark, then you're using a Q's product, and you shift left and right.
That is-
And again, if you're chilling and you're waiting, bust out a multiple choice test or, you know, do what you got to do.
And for this one here, I was also confused about this number 36.
Yeah, it's kind of fun. So the idea
Zero
is
with the law of thermodynamics.
not creative.
Yeah.
Meaning.
Ideal.
Meaning, the ideal gas law assumes that it assumes that there's zero intermolecular force. And it also assumes that our atoms and molecules take up literally zero volume. Okay, that's
I do know.
so in this instance, they're saying, okay, according to the ideal gas. But when they make certain way they're greater, the pressure is greater than we would expect. More mass of argon. This has no bearing. The only gas property is more mass effect.
Because I was thinking about like momentum possibly, and then I was like, well, momentum is probably going to stay the same, so pressure is something.
Correct, and yes, so this is
No,
not.
it's further.
Significant number of popular. No chance, no chance, because argon is no, these things react with nothing. Direct proportion one hundred and 5%. Now, this
Well, I'm there all the time.
meaning like, in an ideal gas, the real gas that is attracted. The argon molecules would be attracted, or say argon atoms would be attracted to each other. And this is much more correct, exactly. That can be- This is counterintuitive. If they said it was pressure, it's water.
Oh,
But they said it was radiation, and this would be force. making this true up to my volume. This is the president. The immediate gas law doesn't account for the actual physical state.
What does that mean?
So think about how 10 meters, and I'm assuming that I have 10 meters. Okay, that's all well and good. But now let's say I have atoms. And let's add a 0.5 of I'm plugging 10 into my ideal gas line. In reality, it's 9.5. Volume 10. Am I correct?
I'm not.
Okay, that's a little bit confusing.
A little bit, yeah.
What do you know?
Yeah, that's a very tricky question. But yes, but by effectively ignoring the volume of the atoms themselves, we have less volume than our flexibility function. And that decrease in volume results in a
The student continues the experiment for an additional minute. For beaker 2, will the mass of H2O2 consumed during the second minute be greater than, less than, or equal to the mass of H2O2 consumed during the first minute? Explain your answer referring to the data in the table. This is literally like an ACT question. I don't think this is AP chemistry right now. This is ACT science section. Here's what I mean. Whoops. You've got a graph, or you've got a data table, right? And this happened for 1 minute. Now, let's look at the trend as the minute proceeds, right? Okay, I lost 0.13. I lost 0.12. I lost 0.11. I lost 0.10. I lost 0.08. I lost 0.07. What's happening? I'm losing less and less and less and less and less. Every 10 seconds that pass, I'm losing less. So if I measure this for an additional minute, would I expect to lose the same? More? No, I'm totally going to lose less. We can see the trend occurring before our eyes. This has nothing to do with like any chemical concept that we've talked about all year. This is interpretation of data. That's all this is. This is an ACT question, in my opinion. So we see the trend going downward. I think the very clear answer, here is, oh wait, I wasn't on the page, I bet. It's just way down there. There it is. The answer has got to be less. Okay, so how do we want to phrase this? I suppose I could rephrase the whole sentence. I'm going to be lazy. Less than. Why? Yeah. The rate of decomposition has steadily decreased. Over the first 50 seconds. Hope that's pretty logical, right? Seems to be pretty easy right in front of our face. We just got to acknowledge the numbers to get that right. E, based on the data, the student claims that the catalyzed reaction has 0th order kinetics. Do you agree with the student's claim? Okay, well that implies that we have to remember what kinetics is. That is where it all goes downhill, potentially. Now, let's think about this. We have, really what we've talked about is 0 order, 1st order, 2nd order in terms of our kinetics, okay? I'm going to use the differential rate law to explain my point. The differential rate law says rate equals K multiplied by the molarity of my reactant raised to a power. You're not going to find it in there. Now, the rate of a chemical reaction is dependent upon the rate constant and the molarity of your reactant. However, in a 0th order rate law, or in a 0th order reaction, that implies my exponent equals 0. So what do I have? I have rate equals K. Long story short, the rate of my reaction is 100% independent of the actual molarity of my reactant. In other words, the rate is constant. The rate's never going to change. In a zeroth order reaction, the rate of reaction will not change, ever. From start to finish, it will be the same. Is the rate of my reaction changing?
Yes.
Yes. Yes. How do we measure rate, by the way?
Just check the difference.
It's like the,
There's the rate loss.
What is rate? What are the units of rate?
Like molarity per time.
Molarity per time. Molarity per second. Molarity per minute, whatever the time unit is, right? How is the molarity changing over the course of time? So there's our molarity, sort of, right? Indirectly, because this is grams of oxygen, but it's, you know, related to how much is being released and how much is reacting. And then here's our time. The rate is changing, without a doubt. The rate is changing. We can see that in the numbers. Is this zeroth order? Can't be. If the rate changes, it's not zero order. So now let's phrase that. Do I agree with the student's claim? I do not agree. Okay. That's enough. You can totally write a second sentence that says a zeroth order process has a constant rate. That would, like, I guess, fully complete our thought. But again, the reader knows that, right? So that's the other part of this, that the reader should very well know that zero order reactions don't have, or have a constant rate. So if you want to write that second sentence, you can. But implying that the rate never changes, or sorry, implying that the rate does change is evidence that this is not zeroth order. Let's see what they say. Disagree. If the reaction were zeroth order, the rate of mass loss, which corresponds to the rate of reaction, would be constant. However, the data shows that the rate of mass loss from beaker 2 is not constant. Make sense? I don't know. First is always a great guess. When you get a kinetics question on the AP test, if you're not sure which order it is and they're asking for an order, guess first. It's a good guess. Actually, and pro tip, if there's anything about half-life anywhere in that problem, it's first order. Half-life questions are always first order. The only type of half-life problem I gave you, and the only type of half-life problem you're going to see is a first order problem.
Like that.
Because if it's not first order, it gets complicated. That's why.
So we should only use that, like, that equation with the 0.693 for.
Yes, no, yes, yes. So in your formula packet, you have a half-life equation. T1 half equals 0.693 over K. It's for first order only. It only works for first order reactions. Half-life equals first order. If that shows up, that's what you want to do. A second student did the experiment using larger volumes of the 9.77 molar hydrogen peroxide. The student noticed that the reaction in beaker 2 proceeded extremely rapidly, causing some of the liquid to splash out of the beaker onto the lab table. The student claims that as a result of the loss of the liquid from the beaker, the calculated number of moles of oxygen produced is greater than the actual number of moles of oxygen produced during the first 60 seconds. Do you agree with this student? Justify your answer. Let's go back to the data. We're claiming that we lost extra mass, right? There was an issue. Our beaker freaked out when we added the catalyst. It reacted so quickly that it spit some of the liquid out of the beaker. And as a result, the student is claiming that that error is going to lead to a greater quantity of oxygen being calculated. Right? That's what they're saying. How are we measuring how much oxygen is produced? By how much mass it loses. So I've lost more mass. What is that going to do to my calculated quantity of oxygen? It's going to be greater than it should be. I think the student is absolutely correct. Normally, we've been disagreeing, it seems like, in a lot of these questions we've done. I feel like we've had a lot of disagreements with the hypothetical students on paper. But this time, they're right. This time, we're absolutely going to agree with what the student has to say. So let's break that down first, and then we'll go into the justification part of it. Do we agree with the student? I agree.
Can we just say like yes or no?
You can. I like using their words just to be snarky.
I can see that.
I mean, I'm not going like full on, like 6th grade essay on you, but you know what I mean? Like, I agree with the student's claim. I didn't go that far. If you want to, go for it. It's kind of fun. I honestly I like answering questions that way just because it feels like it's funny. I don't know. Because like that's kind of like frowned upon once you learn how to write a little more better.
More better.
Yep, exactly. Okay, so we agree. Why? Why do we agree with the claim? Yes. So can I state one sentence in front of that? Okay, cool. I want to make sure I say phrases correctly. Okay, the moles of O2 is calculated based on the mass lost over the course of the experiment. Okay. If we lose more mass, we will calculate more moles of oxygen lost, right? Make sense? So I'm stating where the issue is, right? The issue is that when we calculate moles of oxygen, it's literally based off of how much mass we lose. If we lose more mass, well, then we're going to get more moles of oxygen. Cool? Almost done. What was that? F? Excellent. G. The hydrogen peroxide used in this experiment can be prepared by the reaction of solid ammonium peroxydisulfate, fun, with water. The products are hydrogen peroxide and ammonium bisulfate. Write the balanced equation for this reaction. Now, I have solid NH4 2 S2O8. And this is solid. And they told me what I'm reacting with. They say I'm reacting with water. Okay. And then I'm producing H2O2. And that's going to be aqueous, because we're in water.
In that big one.
Does this work? That's good. Plus, that stuff. Now, that's ammonium bisulfate. You may or may not know this, but it's going to be aqueous, and it's salt. You can dissociate it. Here's the good news. AP's not being picky on the whole dissociation thing with this one. They have 3 possible answers in their answer key for what they would accept. In reality, this should be dissociated, but that feels like a little overkill. So if you just write it out as it is, they'll accept it. Okay.
Really just unless I ask for like the dissociated.
If it was specific, if it was specifically related to like the solubility of salts, then now you got to be more complete, right? And if you know that, then you know that, and you should dissociate it. You know what I'm saying? If you do recognize that this is a salt compound and we're in water and it's going to be aqueous, then you should dissociate it. So they'll give you credit for it. I'll show you the three answers they have in a little bit. Is this balanced? No? You don't have enough oxygen.
Burn.
Sick burn. My comeback skills are solid. Sorry, my brain's not working.
2 on that.
That was better.
Somebody being mean to me?
No, 2 on that.
Is that it?
Yeah.
Looks pretty good, I think.
Yeah.
I think you should just keep it at that. Mr. Brown.
Yeah, looks good. All right, cool. They will accept that. All right, and
Is that it?
you don't need the solids and aqueous and liquids things like I did too. That's actually overkill. What they have is exactly this without the phase tags, or they have this with this dissociated. That's allowed. Or they even go further. They have it where they make this aqueous beforehand, dissociate this, and then cross off the ammonium as a spectator. But in reality, they told me this was solid, so I'm going to use it as a solid. So that's even. I'm surprised they actually accept that.
So if you labeled it as like aqueous, the starting solid, would they want that on that problem?
No.
No.
No, my guess is they completely. If they don't want phase tags in the answer, they probably completely ignore it.
Okay.
So you could put plasma.
It's like that. It's like that.
Probably P. I don't know.
It's like that fifth state of matter that's like when it's really close to like absolute zero.
I forget what that's called. You're talking like what's the condensate? And then like something condensate?
I don't know. There's some sort of like.
I don't know. I'm not going there. Stella.
So for C,
Yep.
like C1, C2.
Yep.
If it says that, are you probably going to be using what you like calculate in one with two?
Decent chance. Decent chance. And actually, this brings me to a different point. This is a good thing for everyone to hear. Some of the issue with these free response questions, right? You've got to remember that when we have these long free response questions, it's technically like one question. The danger of that is that what they give me way back up here, I might need. You know what I'm saying? You literally have to treat all pieces of information within question 2 as like potentially relevant for all possible questions. That's rather annoying because again, this equation from way up top here, we needed to reference like 3 pages in, I think, didn't we? Like with our ratio right here. So you got to make sure you kind of have an open eye to like the intro paragraph, because sometimes they give you something you need in part E 2 pages later. And that's, I mean, it's extremely annoying. Again, it's one of those like things where you got to flip back and find what you need, but be aware if you feel like you're missing something, right? If you feel like, don't I need something for this? Don't I need a K value or something? If you go back to the intro paragraph, there's probably a random K value like hidden in the corner that you're supposed to use on part E. I mean, well, let's hope not. But I mean, like, it feels like that sometimes. My point in saying this is, please be aware that when you take free response questions on the actual exam, what they provide for you way back in the beginning of the intro of the problem could very well be used in the very last chunk of your answers. That is, according to them, that's fair game, right? It's still question 2. So what they provided as the intro to question 2 is fair game throughout the entirety of question 2. Make sense? So the reason why I say that is just to be on your toes and make sure you don't accidentally overlook a piece of information that you may have, that you didn't realize you had because you didn't flip back. Cool. All right, I'm going to stop my recording. You guys are welcome to hang out for a little bit. If anyone has any other questions or any other things they would like to talk about or go over, or you got a multiple choice test you've been chipping away at and there's some burning things that have been bothering you, Or if you just want to hang out for another 20 minutes and get some more test taking in, and you know that you would do it in this environment and not so much in a different environment, please hang out for a little bit. Or you can go, I don't care. As I said the other week, you're free range chickens.